Okay, good afternoon, gang. A few things before we get started. First, you're going to hear a loud buzzing noise. That sucks, I know. It's going to go away soon, though. The video from my previous class is still converting. Zoom automatically runs a conversion after I finish the meetings. And unfortunately, that makes the computer fan turn on because it's a heavy processing thing. So in a few seconds, I promise you that annoying sound will stop. Let me go ahead and swap over to the .cam for the rest of this. So your exam grades are in. As promised. I finished them last night around 8. But I want to say a thing or two about academic integrity. And if your performance on this exam was purely your own, and the work you submitted and the answers you gave were just that of your own mind, then you can tune out to this. But to everybody else, and I know there's a large number of you who cheated on the test, I'm just going to say this, like, don't do it again. All right. You might think I don't notice, but I do. If I left you an explicit note saying, I know you cheated, then especially watch your ass. There are some instances where it's not 100% clear, but I have suspicions. And then there are other instances where it is 100% clear. And I ran into no less than like 5 instances where it was 100% clear that some cheating had taken place. I get that when you're taking a class online and taking a test online, it is overwhelmingly tempting sometimes to have your phone down in your lap or have something to look up or help with the problems. I understand that sense of desperation. I understand that temptation, but we can't have it. It's just not okay. So I did my best here to be lenient and understanding. The first exam was not nearly as bad as this one as far as cheating went. So I don't think I gave you a diatribe about it after the first test, but like I said, I saw no less than 5 instances here where there was some clear, obvious, frankly offensive cheating. And we just can't have that. So if I see anything like this on the next test, especially for anybody that got a little do not cheat comment from me on the test feedback, please look at your test feedback. Then I'm gonna be ruthless about it in the future. It's easy enough for me. I just send an email to Dan Rodkin, say the student cheated on an exam, and then they take it from there. But it's not a pleasant process. It's not a pleasant process for you, obviously, because you have to go to a conduct trial where I also have to go and explain what happened. And then a group of 4, 6, 8 people sit there and deliberate over whether or not this is something that needs some sort of what you call it, retribution, punishment, whatever. The most common form of punishment there is a failing grade in the class with a note on the transcript. So they call it a ZF. And a ZF is bad news. You really don't want that because especially if you're trying to transfer to a university, if someone sees a ZF on your transcript with a note for cheating, then it doesn't necessarily mean an automatic no, but it really hurts your chances. You don't want that. I don't want that. You don't want that. Like, I care about you guys. I want you all to do well. I really do. But at the same time, I have to protect the value of the degrees that we confer at Santa Fe. And one of the most important ways that I'm obligated to protect the value of those degrees is by not allowing cheating to happen. Again, you might think I don't notice it. You might think that it was subtle enough that nobody would notice, but I've been doing this for a long time. And I was a student for a long time. So I'm familiar with what it looks like when somebody is working something out. And I'm familiar with what it looks like when someone isn't working something out themselves. So please just don't cheat, all right? Especially if you got a note from me on this last test saying, I noticed this, don't fucking do it. Really, really don't fucking do it, all right? I don't want any of those nasty things to happen to you that would happen if I did start a conduct trial. Personally, I don't want to have to go through the headache of it. It's a pain in my ass. But I have a professional ethical duty to not allow that to happen. And I take that very seriously. So this is the only warning. This is it. Only warning. If you cheated, I haven't started any conduct trials over this test. Take a deep breath. but know that I saw that shit. I saw that shit, and if I see it again, I will fry you. Don't do it. All right, that's enough. I will stop bitching now. The test grades are in. The test grades were mostly very good. Proud of you guys, how you did overall. There are a handful of things that warrant a little bit of discussion, but those sort of discussions should take place in office hours. So if you have questions or issues with one of the test problems, if there's something there that you're just not quite getting, or you're not sure why I marked it the way I did, come by my office hours. I'll be happy to talk with you about it. Today we're going to continue with logs and exponentials. So on Monday, we introduced the concept of an exponential function. We looked at the graphs of a bunch of exponential function, and we talked a little bit about how to shift the graphs back and forth, up and down, move them around, all that good stuff. I'm going to summarize very quickly. Exponentials like y equals b to the x have graphs looking like this if b is bigger than 1. Here I've left the c off, so c here is 1. This if b is bigger than 1. And looking like this if b is smaller than 1. Both of them have horizontal asymptote y equals 0. Both of them have domain, all real numbers. Neither of them have any x-intercepts. In fact, b to the x is always greater than 0 for all x. So they're both positive and both are monotone. This guy is always increasing, so we call that monotone increasing. This guy is always decreasing, so we call that monotone decreasing. And in particular, they're 1 to 1. And today it's that 1 to 1-ness that I'm going to be interested about, because we're going to start talking about the inverses to these functions. Maybe I should mention the range. I've said it here, they're greater than 0 for all x, but the range is all positive numbers, the open interval 0 to infinity. Okay. We also introduced the number e last time. Which is about 2.71828 and so on. The other name for E is Euler's number, where Leonhard Euler was the fellow who discovered it by looking at the limit by looking at what happens to this expression as n gets bigger and bigger. So for the purposes of this class, really, E is not hugely important. I mean, it's a very special irrational number about which mathematicians care deeply, but the reasons we care so much about it won't be entirely clear until Calc 1. The exponential function built out of base e is very special. So this is called the natural exponential. And I'll tell you, the reason it's so special is because it's equal to its own rate of change. Remember at the beginning of the semester when we talked about average rates of change? Well, if you look at the average rate of change for this function from x equals a to x equals b, that is e to the b minus e to the a over b minus a, you can factor out an e to the b, and you get 1 minus e to the a minus b over b minus a. And it turns out that this piece, as you let a and b get very, very close to each other, goes to 1. So you end up discovering that the instantaneous rate of change for the natural exponential is itself. Now you don't need any of this for this class. You can forget everything that's in the brackets here without any harm coming to you in pre-calculus. But when it comes to Calc 1, that will be an important fact that you will discover and then use quite often. For us, e is just another base. It's bigger than 2, smaller than 3. So e to the x's graph looks like this graph, looks the same as 2 to the x or 3 to the x, lives in fact right in between those. Last time we looked at graphing some transformations of different exponential functions. Today we're going to get the graph of the logarithm function from the graph of the exponential function. I'll define the logarithm for you, and we'll get sort of these basic properties of that graph nailed down. Next week, we're going to be talking about properties of logarithms in some detail. Monday of next week, I'll work through some of that worksheet with you. But your homework this week is mostly about graphs, mostly about picturing these things. And I'll tell you that knowing the graph of the exponential function and knowing the graph of the logarithm function are hugely important things that at Santa Fe historically have been underemphasized. They need to be emphasized more. So your calculus professors will love you if you remember what the graph of the logarithm looks like. So pay attention here. First, the definition. The base b logarithm is defined as the inverse of the base b exponential. That is, if f of x is b to the x, then f inverse of x, the function that exactly undoes b to the x, is the log base b of x. So the b here is a subscript. It kind of sits a little bit below the word log. Log here is not a number. This is not multiplication. It's function notation. This is like f of x, log base b of x. And this definition, while is correct, is not super useful. So an equivalent statement is that when you plug one of these into the other, they undo each other, they cancel. So that means that the base b log of b to the x will always simplify to x, and b raised to the base b log of x will always simplify to x. And then one last way to say this, and you need to be comfortable with all three of these, is that y equals the base b logarithm of x is equivalent to saying b to the y equals x. And it's these bottom two, again, both of which say the same thing. All three of these say the same thing, but the bottom two are the most useful ones. In fact, the very bottom one there is the one that we're going to play with for the most part today when it comes to calculating evaluating logarithms. This is useful for the very basics. This is useful for solving equations. This is useful for getting the graph.
Mr. File Sticker?
Yeah.
What's that word after logarithm is?
Defined.
Okay, thank you.
Yeah, base b logarithm is defined as the inverse of the base b exponential. Okay. So the first thing I'd like to do for you is draw the graph. I'm going to need some different colors here. So I'll use this for our coordinate axes. Let's do it like this. So in the teal here, I'm going to graph the function 2 to the x. Oh, and these look almost identical on camera, don't they? Bummer. All right. So this is f of x equals 2 to the x. And remember, the relationship between the graph of a function and the graph of its inverse you reflect over the line y equals x. So I'm going to reflect this blue graph over this line to get the graph of the base 2 logarithm. So the base 2 logarithm of x has this graph. And just like all the exponential graphs kind of look the same, all the log graphs kind of look the same. The point on the exponential here is 0, 1. The point on the log here is 1, 0. You flip the points over. The point on the exponential here is 1, 2. The corresponding point on the logarithm here is 2, 1. You flip it over. The point 2, 4 on the exponential corresponds to the point 4, 2 on the log. The point over here, which is -1, 1/2 on the exponential, corresponds to this point, which is 1/2, -1 on the log. And the horizontal asymptote y equals 0 that all of these exponentials have corresponds to the vertical asymptote x equals 0 on the logarithm. And just like you change the base on the exponential, not much happens to the graph. You change the base on the log, not much happens to the graph. So you can kind of think of all of your logarithm graphs as looking like this. It continues off and off and off this way, growing, but very slowly. It shoots down here, all the way down to negative infinity. It's undefined over here. So the domain of the base b log of x is 0 to infinity, regardless of the base. The function I've graphed here is the base 2 log, but the base 3 log, the base 5 log, the base e log, all of those have the domain 0 to infinity. The range of the base b logarithm, again, regardless of the base, is all real numbers, negative infinity to infinity. They all have this vertical asymptote, x equals 0. And they all have this basic shape. They all have this x-intercept, 1, 0, all that stuff. You may remember towards the beginning of the semester when we were talking about finding domains algebraically, I talked about these things called red flags, right? Like having a variable under an even root or having a variable downstairs in a fraction. Those are red flags. You have to watch out for them and use them to help you figure out the domain. You now have a new domain red flag. So with logarithms, comes a new domain red flag, namely variables inside logs. So the stuff inside logs, think of it like this way. Must be positive, right? Like the domain of the log is just positive numbers, not 0 and not anything to the left of 0. There is no part of the graph over here. It's all over here. So in order for a log to be happy, its inside needs to be strictly positive. So this is a new domain red flag that we have to add to our existing list of domain red flags. And I could ask you to find the domain of any sort of logarithm function. The trick there is to just set the inside of the log strictly greater than 0. And since you have practice with solving inequalities now, doing that is not especially hard. Yeah, I would be happy to. So an example of this sort, I could say find the domain of f of x equals square root x times the natural log of, oh, I shouldn't use natural log yet. You don't know what that means. Let me say f of x equals square root x times the base 2 log of 1 minus x squared. So I have two red flags here. there's the x under the square root and the 1 minus x squared inside the log. The x under the square root, I know this tells me that x needs to be greater than or equal to 0, right? The stuff that's under a square root can't be negative. The 1 minus x squared inside the log tells me that 1 minus x squared needs to be strictly greater than 0. Right? Whatever variable stuff is inside your logarithm must be strictly positive. This inequality, there's nothing to do. You already know this is just 0 to infinity. This guy, though, we need to solve. And the way we solve this nonlinear inequality is by factoring, finding the special numbers, plotting them on a number line. So the special numbers here are -1 and 1. If you test 0, you'll find that this expression is positive. And if you test anything over here or use the multiplicity trick, you'll find that we're negative over there. So this piece gives us the open interval from -1 to 1. So the domain of this function would be the stuff that makes this happy and makes this happy. So if you draw these on a number line, put -1 here, 0 here, 1 here. That first guy says you can take anything to the right of and including 0. The second guy says, hold up, you gotta be strictly between -1 and +1. So the domain here is the overlap. That's the closed interval from 0 up to open on the right 1. Okay, so with this new function comes a new domain red flag. The inside of logarithms must be positive, regardless of the base of the logarithm. So if you have any sort of variable quantity inside your logarithm, to find the domain, just set the stuff inside the log greater than 0. Okay. Let's get some practice actually computing logarithms. That's the first hurdle here. So without a calculator, let's evaluate these. Yeah, what Lily just said there is pretty much correct. We want to ask, what power must I raise the base to in order to get the inside? Another way to say this is, okay, well, if this is equal to y, that's equivalent to saying 3 to the y is equal to 27. So what power of 3 raised to what number is 27? This is called the logarithmic form. This is called the exponential form. And some of your homework problems will ask you to state in exponential form a logarithm statement or vice versa. But here I just want to know, what is y? So the base 3 log of 27 equals y means the same thing as 3 to the y equals 27. In other words, in order to say what the base 3 log of 27 is, I need to answer the question, what power of 3 is equal to 27? And yeah, in this case, since 27 is 3 cubed, we get that y is 3, i.e. the base 3 log of 27 is 3. What about the second guy here? The base 2 log of 8. We want to think about this the same sort of way. To what power must I raise 2 in order to get 8 out? Yeah, 3 again. This is equal to 3 because 2 to the 3 is 8. What is the base 5 log of 25? To what power must one raise the number 5 in order to get 25? Yeah, Lily's killing it in this chat here. This is 2 because 5 squared is 25. Is everybody else following? So the base b log of some number x is the power to which you must raise b in order to get x. The base 5 log of 25 is the power to which you must raise 5 in order to get 25. All right, what about the base pi log of 1? Yeah, good, Austin and Lily. The base pi log of 1 is 0 because pi to the 0 is 1. And another way to remember this is from that graph. Just like every standard exponential with no coefficient goes through 0, 1, every standard logarithm goes through 1, 0. So regardless of the base 2 log of 1 is 0, the base 5 log of 1 is 0, the base pi log of 1 is 0. The base anything logarithm of 1 is always going to be 0 because any number raised to the 0 is 1. All right, let's keep going. What is the base 2 log of 1/2? Good, -1, because 2 raised to the negative first power is 1/2. So this is -1, and why? Because 2 to the -1 is 1/2. Let's try one more. How about the base 10 log of 0.01? Very good, -2. Why? Because if you take 10 and raise it to the -2, that's 1 over 10 squared, that's 1 over 100, that is 0.01. All right, so these are the fundamentals of logarithms, and you need to be comfy computing them like this. Unfortunately, if the number inside is not a clean power of the base, then the output from these logarithm functions will not be a nice number. And oftentimes that's the case, right? You can think of all sorts of numbers that I could plug into the base 2 logarithm that are not powers of 2. Okay. Let's see. Now we've got some practice with computation. Let's get some more practice with graphing. First, any questions on any of these computations? This is definitely the fundamental thing that we have to wrap our head around here before we can do anything else. Yeah, that's an interesting question. So the natural log is useful for a lot of things. And in certain cases, the natural log will take kind of non-nice number stuff into nice number stuff. But the unfortunate thing is that won't always be the case. So let's introduce the special notation for the natural log and the common log. If you're talking about the base E logarithm, rather than writing log sub E of X, because we use this thing so often, we just call it the ln of X, or natural logarithm. The other special case is base 10. Instead of writing log sub 10 of X, we just write log of X. So if you see log without any base, you know that that's base 10. And if you see ln, you know that that's base E. We should do a couple more examples here, like the ln of e to the 5. What is this? Good, 5. Because the base here is e. So to what power must I raise e in order to get e to the 5? 5. And the log of 10,000? Remember, for this guy, we're asking, to what power must I raise the base, which is 10, in order to get 10,000? So what power of 10 is 10,000? 10 to the what? Yeah, 4. This first one is because e to the 5 is e to the 5. That's not super deep. The second guy you can think of as saying because 10 to the 4 is 10,000. All right. So same business, just slightly special notation for these two special bases. The base 10 log is usually called the common log, and the base E log is called the natural log. Okay. So the graph of the natural log and the graph of the common log, we can look at those as special cases. They look the same. They don't look special in any way compared to the others. So this is the graph y equals ln of x. Still goes through that point 1, 0. And then it also goes through the point e, 1. Still has that vertical asymptote, x equals 0. and doesn't have anything over here. And the graph of the common log is similarly boring, looks the same as the other logarithms. It's just that now you have to go out to 10 before you get up to 1. And we're still going through 1, 0. Okay. So I think the next thing we should really do is talk about graphing transformations of logs, just like we talked about graphing transformations of the exponentials last time. And that is where I'm actually going to leave you guys for this week, is after we've done the graphing of the transformations of the logs, because really the rest of the log stuff has to do with solving equations and log properties. And we're gonna bite into that for real next week. So I want to take the time to really focus on the graphs. So let's sketch the graph of f of x equals the ln of x minus 2. Just like with the exponentials, we have new parent graphs, new parent functions. With the logs, we have new parent functions, and those are the basic logarithm graphs that we've looked at already today. So the parent function here is what? If I want to graph this guy, he is going to be a shifted, flipped, whatever form of what parent function? Yeah, we're going to drag something to the right 2 units. What do I start with? What is it that I'm going to drag to the right 2 units? What is my parent function here? Yeah, which is ln of x, right? We're going to start with the regular natural log and then shift it to the right 2 units, because here I've subtracted 2 on the inside. So the original graph, we just drew this a second ago, looks like this. Going through 1, 0, going through e, 1. So the transformation is shift left by 2 units. So my vertical asymptote, which previously was x equals 0, will now be what? What is my new vertical asymptote? Yeah, good, x equals 2. My x-intercept, which was previously 1, 0, is now going to be what? Good, 3, 0, right? If I take the point 1, 0 and drag it to the left, sorry, drag it to the right. I wrote left, didn't I? I'm sorry. Drag it to the right by 2 units, then we end up at 3, 0. So here's my new x-intercept. It's 3, 0. The point e, 1 is going to come out here to e plus 2. Comma 1. My vertical asymptote is there. So this shifted graph looks like this. My new VA is the vertical line x equals 2. Right, and that's it. This is the graph of f of x equals the natural log of x minus 2. What's the domain here? What's the domain of this function? Good, 3, oh wait, not 3, sorry. Almost. What about this stuff? Yeah, good. Good, domain here is the open interval from 2 to infinity. And we could get that from the picture or by setting x minus 2 greater than 0, right? So to get the domain of a logarithm, again, you set the inside strictly greater than 0. If x minus 2 is strictly greater than 0, you add 2 to both sides and you get x is strictly greater than 2. So the domain is 2 to infinity, which matches up with this picture, right? The graph only exists to the right of 2. There's nothing over here, just stuff over here. There is no point on the asymptote, right? That's why I have a parentheses here, not a bracket. So I'm not including the asymptote in the domain, but I do draw the asymptote on the graph. So am I interpreting the question right, Lily? Okay, cool. All right, let's do 1 or 2 little more things like this where we sketch a graph. And then I want to talk to you a bit about kind of getting ready for what we'll do next week. So here I want to sketch the graph of negative log base 2 of x plus 1. And so again, I would like to identify a parent function and then talk about some transformations that we're going to do to that parent function. Good, yeah, the base 2 log of x is the parent. And his graph we've drawn a couple times now today. Looks the same as all the other logs. Going through 1, 0, going through 2, 1, having this VA here at x equals 0. So what sort of transformations do I need to apply and in what order? Yeah, adding 1 on the inside, we should do that transformation first. So what is that? The x plus 1, instead of having the x on the inside, moves us to the left 1 unit. Yeah, good. And what does the negative on the outside do? Good, it's a vertical reflection. Actually, I'm going to need a little bit more space for this, aren't I? All right, instead of doing this here, I'll do this below. So we want to move to the left 1 unit. So my vertical asymptote is not going to be x equals 0 anymore, but it's going to be over here, x equals -1. And if I just did the left shift, it would look like this. But in addition to that left shift, I'm doing a vertical flip. So the left shifted guy would look like this. Left shifted and flipped will look like this. So 1, 1 gets dragged left to 0, 1, 0 gets dragged left to 0, 0, and it stays there when we flip. 2, 1 would get dragged left to 1, 1, and that would become 1, -1 when we flip. And then, yep, my vertical asymptote. Now I approach it going up. So we flipped over the x-axis. So this is my new graph. To calculate the domain here, from the graph, we can see that it's -1 to infinity, but we could also set x plus 1 strictly greater than 0. That would give me x is strictly greater than -1. So that's the open interval from -1 to infinity. Let's do one more of these transformation things, and then I'll change gear into prepping us for next week. Any question about where this graph or either of these points came from? Yeah, sure. Let me run through this rather than doing both steps at once, one step at a time. So beginning with our parent function, I can first shift left 1 unit. So that moves my vertical asymptote from x equals 0 over here to x equals -1. Takes this point 1, 0 to 0, 0. Takes this point 2, 1 to 1, 1. So this would be y equals log base 2 of x plus 1. That's just doing the left shift. And then if I do the vertical flip, that's the other transformation I need to do because of the negative on the outside here. Flipping over vertically, that doesn't move my vertical asymptote, it still stays there. I'm just going to pick this picture up and spin it over vertically. So my VA is still x equals -1. But now instead of diving off that way, I'm blowing up this way. If I flip this whole picture over vertically, 0, 0 still stays 0, 0. But 1, 1 goes to 1, -1. So my new and final graph will look like this. And this is y equals negative log base 2 of x plus 1. This point being 1 comma negative 1. So first I shifted left by 1 unit, and then I flipped everything over vertically. It's pretty cool stuff. Cool, okay, good. Yeah, I think it's always a really good idea to pick at least a couple points and track them through this whole process. So you see what each transformation does to each of the points you choose on the original graph. It's a really, really wise move when you're trying to graph transform functions, and it can help you out a lot. Okay, one more. How about the ln of 2 minus x? Instead of like x minus 2, 2 minus x. Again, my parent function is just the regular logarithm, ln x, and his graph, we know what that looks like. Going through 1 comma 0 and e comma 1. But what transformations am I going to apply now? Here it's not quite as easy to tell. We had a trick for this that we talked about last time, and then again way back when we first learned about this stuff. That can get you some information, but do you guys remember what we did when we graphed e to the 1 minus x yesterday or Monday? We force factored a negative. Yeah, something very much like that. So I can write this as the ln of negative x minus 2. So now this multiplied by negative 1 on the inside, that's a horizontal flip. And this subtract 2 on the inside, that's a shift right by 2 units. So I've got two things going on, and I'll do them one at a time. If I just do the horizontal flip, I'll get something like this. This is now negative 1 comma 0, and this would be negative e comma 1. And now I will drag to the right by 2 units. So my final graph the point negative 1 comma 0 is going to get dragged right by 2 units to 1 comma 0. The point negative e comma 1 is going to get dragged right 2 units. Since e is like 2.7, negative e is like negative 2.7. So this is going to be negative e plus 2, or 2 minus e, comma 1. And the resulting graph here will look like this. And yeah, it'll shallow itself out a little bit as we go out further and further. You could write it as negative e plus 2, or approximately negative 0.718. And Austin, yeah, you're correct with the domain. The domain here is negative infinity up to 2. We can see that by setting 2 minus x strictly greater than 0. Add x to both sides and you get 2 is greater than x, and then flip it over and you get x is less than 2. Or you could see from the graph that, yeah, negative infinity up to, but not including 2. All right, I want to take a brief look at your homework and make sure there isn't something I'm forgetting here, but I'm pretty sure that I just slapped you guys with a bunch of graphing problems and concept stuff this week because I wanted to save the more challenging computational stuff for next week. So just a quick review here, and if I am correct in my memory, then I will introduce next week's material. Let's have a quick check. Lots of this, and this, and graphing, domain, and range, and transformations, and yay, all this good shit. Matching graphs, computing logs, evaluate in this form or that form, use the definition, sketch by plotting points, sketch by transformations, nothing else going on, right? Yeah, no, okay, good. So then next week, we're going to begin by asking the following question. How do you solve, or how does one solve the equation 2 to the x equals 3? If you look at the graph y equals 2 to the x, (0, 1, 1, 2, and out here you've got 2, 4. In between 2 and 4, there is 3. And since this graph is continuous, somewhere here between 2 and 3 is the x that I want. It's a challenge because 3 is not any sort of obvious power of 2, right? Like if this was a 4, I would say, oh shit, well 2 squared is 4. Or if this is a 1, I would say, oh, 2 to the 0 is 1. But writing 3 as a base 2 thing is challenging. Unfortunately, taking the xth root of both sides, that's a very good intuition, won't do the job because then you just get 2 equals 3 to the 1 over x. So while if the power here was a constant and the variable was in the base, that would be the move, right? Is to undo the power by taking the appropriate root. But unfortunately here, if you take the xth root of both sides, that doesn't work. It is equivalent to saying 2 equals 3 to the 1 over x. But is that any easier to solve? Yeah. So Fabrice has got it here. We're going to use a logarithm. What we need to do is undo the 2 to the x function. Well, remember, the base 2 logarithm is designed to undo the 2 to the x function. That's literally what it does. So while this is correct, it's not helpful. But what is helpful is to think about logarithms. So if I take the expression 2 to the x equals 3, and I apply the base 2 log to both sides, then the base 2 log of 2 to the x is x. And over here, I just have the base 2 log of 3. And Fabrice, it turns out this is equivalent to what you suggested, because through something called the change of base formula, the base 2 log of 3 can be thought of as the natural log of 3 over the natural log of 2. Logarithms undo exponentials. That's what they do, right? The base b logarithm is defined as the inverse to the base b exponential. So if your variable is trapped inside an exponent, the trick is to take the appropriate logarithm on both sides. It turns out that because the algebra properties of logarithms are what they are, it really doesn't matter which base logarithm you take. And that's why you hear people say like, oh, the natural log is the only log we care about. That's why the only button on your calculator, if you have a TI-83 or something, is just the ln, or maybe an ln and log button. Because the other buttons, the other logs, sorry, they're all constant multiples of the natural log. So I want to reiterate that worksheet that I sent out last week is something that I want you guys to put some real time into. The homework this week is not especially challenging, which means you'll have a little bit of extra time after you finish it. And I would like you to put that time into that worksheet. And next week, next Monday, together, we're going to work through some of those problems. I might put you guys into groups and do a little bit of group work, or I might set up some polls so that you guys can answer questions through a poll during class. But we're going to be working through some of those problems together to make sure everybody really understands what's going on. The log properties are things that are easy to remember wrong. They're easy to make little mistakes with. So the more we practice, the easier it will go. We want to do another example of like solving an equation like this or graphing. Sure. Yeah, I mean, if I wanted to solve well, let's do it like this. How about, no, more fun. How about 10 to the x minus 1 equals 30. So you know that 10 to the 1 is 10, 10 to the 2 is 100. So somewhere between 1 and 2, there is a number so that 10 to that number is 30. I want to know what number can I subtract 1 from, then raise 10 to that power to get 30 out. And the slick move here is to take the common log on both sides, the base 10 log. And just like the base 2 log of 2 to the x simplifies to x, the base 10 log of 10 to the x minus 1 simplifies to x minus 1. So here you would get x minus 1 equals the common log of 30. And then you would just add 1 to both sides. Now you need to respect the notation. This is not the same as the common log of 31. I can't put the 1 inside or anything like that. Our answer is just this. Or if you want it as a decimal, it's about 2.47. Call it 2.47, 2.477. And you can play with this. If you take 10 and you raise it to the 2.4, my hands. Take 10, raise it to the 2.477 minus 1. This is the same as 10 to the 1.477. And if you plug this into your calculator, you get 29.99. All right, so I'm just rounding here, but you get something very, very close to 30. I will talk about when to use log, when to use ln, when to use different things next week. The truth is you can actually use whatever logarithm you want when solving these equations. You could take the base 10 log, the base 2 log, or the natural log of any of these. But in order to understand why that works, we have to talk more generally about the algebra properties of logarithms. And that's precisely what next week's lectures are about. So I will leave it for here, saying if you want an answer to that question right now, I encourage you to check out that logarithm worksheet, or of course you can read the textbook. The textbook is pretty good. But yeah, because of the algebra properties of logarithms, specifically, regardless of the base, the log base b of a to the x will always be x times the log base b of a. Powers here can come down. You can actually use whatever base log you want to solve equations like these. Alrighty, gang, this is where I'm going to leave it for today. I do have an office hour this afternoon, 3:30 to 4:30, normal place in Zoom. Tomorrow, I'm going to have an in-person office hour on campus from 9:45 to 11, but I will not have my normal online office hour because after that in-person office hour, I'm going to go vote. I do not know how long those lines are going to be, but I will do an online office hour when I get back. I just can't tell you right now exactly when that is. So if you want to talk to me and you can't come today, either come in person tomorrow at 9:45 A031D, or watch for my announcement tomorrow afternoon when I get back. All right, work on those homeworks. Make sure you remember the graphs of these logarithms. Next week, we're going to be playing around with the algebra properties. And that is all. Take care, guys.